So picture this. It's the absolute final moments of a massive global event, let's say a World Cup final. You, along with millions of other people, are glued to your screens, completely expecting instant, flawless video. But making that actually happen, well, that requires some of the most insanely sophisticated, totally hidden architecture on the entire internet. Welcome to today's Explainer, where we're going to pull back the curtain on exactly how this works.
I mean, really think about the scale for a second. Imagine 50 million people all hitting play within the exact same 60-second window. That massive, ridiculous spike generates something to the tune of 300 terabits per second of traffic. And the crazy expectation we all have, it has to run without a single buffering wheel. No visual glitches, nothing. And that goes whether you're sitting at home on a crazy fast fiber connection or you're stuck on a spotty 4G network on a moving train.
Because of that immense pressure, we kind of need to redefine what we're actually looking at here. Live streaming, it is not merely a simple video delivery task. It is a planet-scale distributed systems problem that is just cleverly disguised as entertainment. It is literally the internet's single largest real-time fan-out workload. To pull this off, engineers have had to completely master advanced caching, sharding, and incredibly intense backpressure flow control.
Okay, let's dive straight into this. Here is the architectural pipeline we are going to uncover today. Number 1, the 50 million viewer problem. Number 2, chunking video with HLS and ABR. Number 3, inserting ads without glitches. Number 4, scaling delivery via multi-CDN. Number 5, the control plane and handling failures. And finally, number 6, master patterns.
Right, let's start with section 1, the 50 million viewer problem, and why this goes way beyond basic video delivery.
Moving right along to section 2, chunking video, specifically looking at HLS and ABR. I like to call this part the HTTP illusion.
So, to survive the totally hostile, unpredictable environment of the open internet, you obviously can't just send one giant continuous video file. It would fail constantly. Instead, we create an HTTP illusion using something called HTTP live streaming, or HLS, and it relies on two very specific text files. First up, you have the master playlist. Now, this file is immutable during the stream. It doesn't change. You can think of it just like a menu of all the available quality variants, your 1080p, your 720p, the whole lineup. Then you have the media playlist. Now, for a live event, this file is append only. Your video player is continuously pulling this list, asking for new tiny little video segments. By essentially transforming a continuous video stream into highly cacheable text files and standard HTTP requests, we can leverage global CDNs to actually make this massive scale economically viable.
But there is a hidden, absolutely non-negotiable constraint to making this whole thing work. Segment boundaries must strictly align with keyframes, also known as iframes, across all of those quality variants. See, video encoders, like FFmpeg, they have to place these keyframes totally predictably. Why? Well, if your player tries to seamlessly switch from high def down to standard def midstream and those keyframes don't align perfectly, boom, the viewer gets hit with an ugly black frame or a horrible visual glitch. Predictability here is quite literally everything.
And once that beautifully predictable video ladder is ready to go, the player's adaptive bitrate, or ABR, decision loop takes the wheel. It's a continuous, fascinating little cycle. First, the player downloads a segment and measures the actual throughput it just got. Second, it estimates the available bandwidth. Third, it checks how much buffer length it has safely stored ahead. And finally, based on all that math, it chooses the very best quality variant for the next segment. What you really should take away from this is that the player is making decisions to optimize for the absolute worst-case network, not the average. It dynamically, constantly negotiates quality versus bandwidth just to make sure your video never stops playing.
Let's jump to section 3, inserting ads without glitches. This brings us to the SSAI pipeline.
Now, what's really interesting about this is that monetization is easily the biggest friction point in the entire streaming world. You want to show ads without ruining the caching infrastructure. Look at the sheer orchestration involved here in server-side ad insertion, or SSAI. It kicks off with a broadcaster queuing up an industry-standard SCTE35 ad marker. Right away, a manifest manipulator intercepts this, reaches out to the ad server, and gets back what's called a vast response. But step 4 is the really crucial part. That ad has to be transcoded on the fly to perfectly match the live stream's exact bitrate ladder and those all-important keyframes we talked about earlier. Finally, a discontinuity tag is added to tell your player, hey, reset your decoder for a second. Through this whole pipeline, the ad basically disguises itself as just another perfectly normal, seamless segment in the video stream.
To really understand why we do this, let's contrast SSAI with the older method, Client-Side Ad Insertion, or CSAI. On the left side, SSAI is magic for the viewer, zero buffering, and it's highly resistant to ad blockers. But it introduces a massive architectural headache. You now have to generate a completely unique, personalized manifest for every single user. It totally breaks edge cacheability. Meanwhile, on the right, CSAI is way simpler to implement and super cacheable because the player SDK just handles it, but it causes really annoying visible glitches and is incredibly easy to block. Ultimately, for premium 50 million viewer events, the flawless seamlessness of SSAI wins every single time, even though it demands a staggeringly huge back-end infrastructure to pull it off.
All right, Section 4, Scaling Delivery via multi-CDN. This is where the heavy lifting happens and where the bytes actually live.
Now you might be thinking, hey, for 50 million people, let's just use one unimaginably giant CDN, right? Well, actually, no. Notice this typical multi-CDN traffic split. We're looking at 80% of the traffic routed to a primary CDN, but a solid 20% is intentionally routed to a secondary one. Why on earth would we do that? Because that secondary CDN has to be kept warm. Think about it. If your primary CDN has a sudden catastrophic outage, a backup CDN sitting at 0% utilization absolutely cannot just instantly absorb 100% of your planet-scale traffic. It would just instantly crash. So you must have active failover and continuous, real-time performance benchmarking running at all times.
And as we push all these petabytes of data around the globe, we have to make sure only authorized users are getting them. Enter token authentication. If we tried to have a central server authenticate 50 million viewers every single time their player fetched a new 5-second chunk of video, we would literally melt the origin server. It's just not possible. So security has to be completely self-contained. We use HMAC-signed, time-limited security keys. This way, the validation happens statelessly, right out at the furthest CDN edge, far away from our fragile core infrastructure.
Which transitions us nicely to Section 5, Control Plane and Failures. Let's look at what the streaming provider is actually doing behind the scenes.
So the crucial point here is a massive separation in modern architecture, the data plane versus the control plane. The CDNs, they represent the data plane. They do all the grunt work, actually pushing the massive heavy volumes of video bytes to the viewers. But the streaming provider itself, they operate the control plane. They act purely as the brains of the operation, handling user identity, issuing those security tokens, running the complex ad decisioning logic, and dynamically routing traffic between the different CDNs. They orchestrate the entire global movement, but they very rarely push the actual video bytes themselves.
Of course, operating that brain means you have to plan for exactly when, not if, things break. Let's get real about operational failure modes. If a video encoder simply dies in the middle of a game, our segment lag metrics will detect it instantly, and a hot standby encoder takes over in under 5 seconds. If the origin server faces a sudden overload, we'll see a massive P99 latency spike, and engineers will immediately mitigate it using origin shields and request coalescing. And if an entire global CDN goes down, real user monitoring detects the sudden spike in error rates, and the system dynamically reweights the traffic over to that warm backup we mentioned earlier. This is exactly how principal engineers design these mitigations to keep the overall platform availability sitting at an astonishing 99.95%.
And that brings us to our final part, Section 6, Master Patterns and our System Design Takeaways.
Everything we've unpacked today really synthesizes down into some incredible, overarching master patterns. And this brilliantly illustrates how modern tech is built. Separate your control plane from your data plane. Resolve the tension of caching by completely splitting your personalized manifests from your heavily cacheable raw content. Keep your central servers breathing by validating stateless authentication right at the edge. Never ever trust a single dependency. Always employ active multi-vendor failover. And always build robust circuit breakers around every single dependency you have. The amazing thing is, these exact same principles apply just as much to building real-time social feeds, global payment processing, and massive IoT platforms as they do to video.
Which brings us to a final thought I want to leave you with today. The very next time you click a simple button online and something happens instantly and perfectly, ask yourself, what other simple internet interactions are actually massive, completely chaotic, multi-vendor distributed systems operating in disguise? Once you start recognizing these underlying master patterns, I promise you, you will see the modern internet in a completely different light.
Thank you so much for joining me for this explainer. Keep building and stay curious.